This is an introduction to power functions and polynomials. Polynomials are an important class of functions because they do a good job of modeling things like area and volume. They're also used in regressions, which is where we try to fit a function into data that's collected perhaps in the laboratory. And polynomials will also be used in more advanced math down the road as you study math later on. Power functions are the pieces that make up polynomials. And there's a lot of things about power functions that tell us about the more complicated polynomials. And so we'll start off our study by looking at these power functions specifically. A power function is a function that has the form f of x equals some number a times x to the power of n. And so let's talk about these numbers a and n. N, the exponent, can be anything from 0 to 1 to 2, 3, and so on. Okay? And in reality, n can be negative, n could be a fraction. Those are all legitimate power functions, but for what we're doing, especially heading towards studying polynomials, these numbers 0, 1, 2, 3, and so on are the numbers that are going to be the most important for us to take a look at. The other number here is a. This number is called a coefficient. And a coefficient is nothing more than a number that multiplies a power function, multiplies a function, and it's going to have a role in determining various aspects of the polynomial and the power function. A could be really any number, any real number. It could be positive, it could be negative, it could be 0. And each of these particular cases will have implications for the polynomial that it is part of. Let's look at some basic properties of some real fundamental power functions. We'll start off with x squared. And we're pretty familiar with x squared. That gives us a parabola opening upward, as we can see here. And here's a table of some values near the origin. So nothing too new or striking here. I want to also show you if we have a coefficient of -1, in other words, our function is negative x squared, we know that that's going to be a reflection over the x-axis. All of the positive values that are generated by x squared become negative values because of the negative sign in front of the function. So what's important to note here is that not only does that give us a reflection, but as we're going to see, we want to know what the ends of these functions are doing. In other words, what is the end behavior? And we can see that in this case, our end behavior is that the ends both go up and to the right and to the left. And here they go down to the left, down to the right. We go over to x to the 4th power, and we see a lot of similarities between these two graphs. The difference is, of course, that we're raising the number to the 4th power instead of the 2nd power, and so we expect our y values to be different. And if we were to really look at the graphs accurately, we would see that this parabola-looking type of a function here actually is different from this one. It's going to be a little flatter on the bottom, more vertical on the sides as the numbers increase faster. You can tell the difference between these numbers and these numbers. Once again, if we put a negative sign in front of that, we reflect this downward. Now what I want to show you here, just as a bit of a preview, is that when we have an even number for the exponent, 2 or 4 in these cases, our end behavior really looks the same. Okay? When we have a positive coefficient, our ends will both go up. When we have a negative coefficient, our ends will both go down, and we see the same thing here with the coefficient, or the exponent rather, of 4. Okay. Now contrast that with these power functions. X cubed, this is an odd number, and we can see that the ends go in opposite directions. So this is a key feature of power functions. Even exponents give us ends that go in the same direction. Odd exponents, here's x to the 5th, that's also odd, give us ends that go in opposite directions. Not only that, if we have a negative coefficient, the graph is going to flip. So instead of going to the right and up, we're going to go to the right and down. Instead of to the left and down, we'll go to the left and up. And so you can see that the graphs of x cubed and x to the fifth are very similar, just as x squared and x to the fourth were similar, except now that our end behavior is different. Odd exponent, opposite end behavior. Positive coefficient rather, we're going to go from quadrant 3 to quadrant 1. Negative coefficient will go from quadrant 2 to quadrant 4. So let's explore these concepts in a little bit more detail. Here we have x squared. So we know that this is an even exponent, and so we expect that we have ends that go in the same direction. Notice that because this is an even exponent, we have even symmetry around the y-axis. Remember that an even function has a reflection around the y-axis, so the left half and the right half look like mirror images of each other. We see that as x goes to positive infinity, in other words, as we move this way along the x-axis, our y values go to positive infinity. Okay, y values are over here, f of x. And as x goes to negative infinity, the y values also go to positive infinity. So this end behavior summary is very important, and we'll see that this is going to be the same for all even power functions. So if we were to write the general polynomial expression for x squared, we would see that we have some coefficient a times x squared, a2, okay, plus a coefficient a sub 1 times x plus a coefficient a sub 0. Now we can think about x to the 0 power here because we know that any number raised to the power of 0 is equal to 1, and that this x is really x to the 1 power. So we see that with a polynomial, we're going to be adding power functions, and we're going to have a different power function going up as high as we need to for the polynomial. So in this case, we start at 0, we go to 1, we go to 2. This is what's called a degree 2 or a second degree or second order polynomial, because the degree, the highest exponent in the polynomial, is 2. And I know I've drawn on it here a little bit, but you can see that that's 2. In fact, I'll erase that. X to the 2 power, this is the highest exponent that's in the polynomial. That is the degree. And so the degree of the polynomial will be very important too. The leading term is the entire power function that makes up the term that has the highest exponent, the highest power of x, the degree. So the leading term is going to be with the x squared for this power function. And so for this example of a polynomial that I put right here, we can see that it is a degree of 2, and we have a leading term of negative 2x squared. The leading coefficient is just the coefficient that goes with that power function, and in this case, that's negative 2. So these three things are going to be important in analyzing polynomials. What is the highest exponent, the degree? What is the entire leading term? What is the power function that is associated with the highest exponent? And what is the number that's in front of that thing? If we go on, we can see that our x cubed is a third degree polynomial, or degree 3. It has odd symmetry. As we go to positive infinity along x, f of x or y goes to positive infinity. And as we go to negative infinity along x, f of x, or the y value, goes to negative infinity. So we have opposite directions on the ends for the end behavior. This is the general polynomial. Again, we have a sub 0, and you can think of x to the 0 power here if you like. a sub 1 times x to the first power, a sub 2 times x squared, and then we have a sub 3 times x cubed because this is a third degree polynomial. We can continue this pattern with fourth degree. We see that this is even, so we expect that the ends go in the same direction. This is a degree 4. Its leading term is 2x to the fourth for this particular polynomial. Its leading coefficient is 2 because that's the number that's in front of the leading term being the one that has the highest exponent, which is the degree. And finally, for x to the fifth, we see again a continuation of the pattern. We have odd degree. Our ends go in opposite directions. We have a degree of 5. Leading term is the one that has the x to the fifth. That's negative x to the fifth is the leading term. That means that the leading coefficient is negative 1. A few other things about these particular power functions and polynomials. The number of factors, and we'll see what factors means after a bit, but if we look at the factors, break this down into factors, we will see that the maximum number of distinct factors we can have is the same as the degree. Okay, so this may have 2 factors, x cubed may have 3 factors, and so on. How about turning points? If you look at the graph, you'll see that a degree 2 polynomial, which is a parabola, has 1 turning point, which is right here. X cubed might have as many as 2 turning points. Okay, so this is the maximum number of turning points, but if we go back up to our parent function, we can see that this graph, x cubed by itself, does not have any turning points. Okay, it just moves smoothly through the origin. So the number of turning points is actually a maximum. It can have up to that number, but doesn't have to have that. Fourth degree polynomial could have 3. So you see it's the degree minus 1. Number of turning points, the maximum it could have is 1 less than the degree. So degree 4 polynomial would possibly have 1, 2, 3 turning points. And same idea with the degree 5, could have 1, 2, 3, 4 turning points. So if I were to graph these particular polynomials, I would get graphs similar to what you see down below here with these various characteristics. Again, looking at the end behavior. Here I have a leading term that has x to the fifth. This makes it odd, so my ends are going in opposite directions. Because I have a negative leading coefficient, I'm going from quadrant 2 to quadrant 4, opposite directions, but compare with this odd polynomial where my leading coefficient is positive. I'm going from quadrant 3 to quadrant 1. Again, opposites, but flipped, if you will, from these. Negative to the left, positive to the left. Positive to the right, negative to the right. Same idea with the even degree polynomials. In this case, the ends go in the same direction, but because I have a negative leading coefficient, these go down. Positive leading coefficient, these go up. So this is a quick summary of a lot of the features of polynomials and power functions. In further videos, we'll take a look at these in a little bit more detail and see how they relate.